In this work, we discuss adaptive safe control for driving in uncertain environments. According to the US Department of Transportation, approximately 23% of all motor vehicle accidents each year can be attributed to driving in adverse weather conditions, which includes icy roads causing slipping. Inclement weather poses a challenge for both human drivers as well as autonomous vehicles. This is because tire parameters change significantly during the operating period. And these changes in parameters can drastically affect the system dynamics of the vehicle. And therefore, any control strategy must have the ability to quickly adapt to meet these changes to guarantee safety requirements. So here's a demonstration of what happens when a vehicle is driving in slippery conditions. Here we've provided the vehicle with a reference trajectory to go forward and take a right turn at the corner. However, we see that as soon as the vehicle starts to slip, the controller loses traction and is therefore unable to complete its objectives. So our goal is to design a control algorithm for autonomous vehicles that is robust, adaptive, and computationally efficient, whilst guaranteeing long-term safety and be able to work in large uncertainties and changing environments. Some of our related works include probabilistic safe controls, which tends to be over-conservative due to its tendencies to model errors in the worst case fashion. There are control barrier and Lyapunov functions, which have problems in integrating competing safety versus performance objectives due to the fact that most control barrier functions are handcrafted. And we have reachability-based safety methods which suffer from the curse of dimensionality and are also highly stringent in terms of their control action. So first, we guarantee long-term safety. And we do this by computing what is called as a safe probability. And the safe probability is a metric that we use to assess how close we think the vehicle is to committing a safety violation. And in our control, we essentially aim to clip the safe probability within a certain level, which is characterized by a parameter called as the safety tolerance level, shown as epsilon in this plot. We see that our safe controller for a given epsilon manages to keep the safe probability within that specified level. Whereas we see that for the model predictive controller, it very quickly reaches 0. Here we examine the total tire forces for each of the 4 tires of the vehicle. Here we see that for the model predictive controller, the forces quickly saturate and hit the maximum saturation force and the vehicle starts to slip. Whereas for our controller, for all 3 tolerance parameter levels, we see that the forces remain within the specified grip level. Further, we also provide better performance trade-offs. Here we examine this trade-off by considering the cost, that is the deviation from the reference trajectory, and the safety, that is the satisfaction of the tire force limits. We see that, as expected, increasing the safety tolerance causes the performance to increase. In other words, having a more stringent safety requirement causes the performance to decrease. However, we see that for our method, this degradation in performance is much more graceful. Whereas for the model predictive controller, we see that not only is that the overall cost is higher, but also the steepness of the trade-off is much more apparent. We have lower computational costs, and this is due to the fact that if we consider model predictive control, the computational cost is OH3, where H is the prediction horizon of the MPC. Whereas we see that the safety is independent, more or less, of the prediction horizon. And therefore, we show that safety will not be compromised, even with shorter outlook horizons. Well, how does our method actually work? Well, on the right, we have the traditional control barrier function, and on the left, we have reachability methods. Control barrier functions characterize what is called as a safe set, and the safe set is defined as the super level set of a function phi of x. And the goal is to induce forward invariance into the safe set, such that once the system's trajectories start in the safe set, they remain within the safe set for all t. And on the left, we see reachability methods. And in a reachability analysis, we examine a receding horizon time. That is, we consider a region and we assess what are all the possible times we can approach that region in a receding fashion. And what we've done is we've chosen the best of both worlds. And what we essentially do is we compute what are called as forward rollout trajectories. That is, we simulate the vehicle's trajectory over multiple episodes, and we assess which of these trajectories enter the unsafe region. And using this computation, we are able to calculate the safe probability. And using this safe probability, we are able to construct a new safe set that is now in the probability space instead of the state space. And we guarantee forward invariance on this safe set in the probability space. And therefore, we are able to guarantee long-term safe probability over any horizon that we choose, given an estimate of our uncertainty variables. And therefore, we are reliable. So how do we actually impose this forward invariance in the probability space? We compute the time derivative of the safe probability, which is essentially an infinitesimal generator. And we impose the following inequality on this time derivative. And therefore, if this time derivative satisfies this inequality, then it is proved that our safe set will be forward invariant. And so we can essentially break this time derivative down into a set of gradients and Lie derivatives in terms of the system dynamics. And the good thing is that these parameters are going to be constant given our knowledge of the system dynamics and the state estimate. And therefore, we see that this time derivative is linear with respect to u. And therefore, we arrive at a linear matrix inequality. And most QP solvers perform extremely well with linear matrix inequality constraints. And therefore, we guarantee very good efficiency. So our actual quadratic program involves a deviation from a given nominal controller, whilst guaranteeing the aforementioned the aforementioned inequality constraint. And therefore, we have modularity because this nominal controller can be anything from MPC to pure pursuit or Stanley, anything. And therefore, we have good modularity. In conclusion, we have a safe control strategy for vehicle tire force control with provable long-term safety guarantees and the ability to deal with uncertainties and adapt to changes while providing good trade-off between performance, safety, and computation. Thank you.